Okay, so maybe we can begin. So welcome everybody to the IMSc Algebraic Combinatorics Seminar. This week we have Arvind Ayyer from the Indian Institute of Science, Bangalore, who's currently stuck in Sweden. And he's going to talk about combinatorics of an exclusion process driven by an asymmetric tracer. But just before he begins, I'd request you all to keep your mics on mute. However, if you have any questions, you can just unmute your mic and interrupt the speaker and ask him yourself. So, so with that, yeah, let me hand it over to Arvind.
Okay, so thank you for this kind invitation, and I'm virtually at IMSc. Can you guys can you see my mic? I mean my cursor?
Yes.
Okay, so I'm virtually at IMSc. I'll be using that as a pointer. Anyway. And so I want to talk about something that I've been working on for the part of the last year. This is partly probabilistic, partly combinatorial. So I'm addressing a mixed audience, so please feel free to interrupt me at any time. And the connection at this hotel is also a bit iffy. So if you find that I'm inaudible at some point, please ask me to repeat. Okay, so here is the plan. I'll first introduce the model and then give you some motivation and history. Then I'll give the combinatorial formula for the stationary distribution, and then talk about the partition function and its relation to the combinatorics of the Stirling numbers. And then I'll I'll show you some results about correlation functions, interesting ones, and particularly I'll focus on something which I'll make clear called the tracer's point of view. And if there's time at the end, I'll explain a little more about the asymptotics. Okay, so here's the model. So you consider that there are L sites, boxes if you like, with periodic boundary conditions. That is to say, the Lth site is also connected to the first site. So these are arranged in the form of a circle. That's why I've written Z mod Lz. Now on each site, you can have at most one particle. There are two kinds of particles. So there's the ordinary particle or regular particle, which I'll denote by 1. And there's one special particle, which I'll call the tracer, and I'll denote it by 1 hat. So each site, just to repeat, each site can have at most one particle. So L is at least as large as n plus 1. And the remaining sites, empty sites, will be vacant, will be denoted by 0. Okay. So now
a particle is an occupied site. I mean, they are indistinguishable otherwise, right?
Yes, exactly. Yes. So all n particles are indistinguishable.
So by a particle, one can understand it's just an occupied site. So
yes.
N sites are occupied.
N plus 1.
Okay.
Because this tracer is also a kind of particle.
But the tracer can be at a site where there's an ordinary particle.
No.
It cannot.
So,
okay.
No. So yeah, thanks for that. Okay. So every site can contain at most one particle of any type. So either ordinary or tracer. Yeah. Is that okay?
Yeah. So you have n plus 1 occupied sites, out of which one you distinguish as 1 hat.
Exactly. Okay, good. So now the dynamics, so this is going to be a Markov process. So so the dynamics is governed by it's a continuous time Markov process, but without getting into too much details, I can roughly describe what's going to happen, what the dynamics is as follows. So suppose there is a particle and a vacancy adjacent to it, either on the left or on the right, then the particle will hop to the adjacent vacancy with rate 1. So these 1 above and below the arrows correspond to rates of the process. So if you want to think about it heuristically, the one way of thinking about it is that at each time dt, there's a probability 1 times dt of the particle hopping. So it's a heuristic and useful way of thinking about it. So that 1 times dt corresponds to this one. So this is called symmetric exclusion.
This is a continuous time thing?
Yes.
Okay.
So that's why in time dt you can make that hop. So the more probabilistic way of thinking.
One more question. So it has to choose between left and right, no? If both are
right. So one way you can think about it is as follows. So you attach exponential clocks to each edge, that is to say each boundary between two connected sides, two neighboring sides. And then if that clock rings, then you choose with probability half to make the jump one way and half the other way.
Okay, so since there are a lot of non-probabilists here in the audience, basically what you're saying is that you have you choose an exponentially distributed random variable, and after that much time, you either move to the left or to the right with probability half.
Yeah.
Okay.
But only one of them can happen, right? So
yeah.
So either it's a 1, 0, in which case that you move this way, or it's a 0, 1, in which case you move the other way. If it's a 0, 0 or a 1, 1 or something, nothing happens. Right?
So by the rate, you just mean the expectation of the exponential random.
Yes. Yes.
Okay, thanks.
Okay, so this is called symmetric exclusion. So it's symmetric in the obvious sense that motion forward and backward is the same for the ones, for the particles. And it's exclusion because every site has at most one particle. But the tracer is special. So it has similar dynamics as before, except that it moves asymmetrically. So the tracer moves to the right, or if you want clockwise, with rate p, and counterclockwise with rate q. And of course, it can only move to a vacancy. So if a tracer is adjacent to a regular particle, then they cannot interchange. Okay, is that clear? Is there any questions, please?
Yeah, one more question. So it's essential here that you use exponentials, right? Because they have to be memoryless.
Yes, yes. So for continuous time processes, they have to be governed by exponentials.
Because all kinds of things could be happening, and then
yeah.
There was a 0 to my left, and then after some time somebody moves in there, then.
Yeah. Right. So because it's continuous time, also at most one transition will take place at any given time. So it's not like two things can move. That's and
probably 0. Yeah.
Yeah. So I mean, all this is just. I'll come to the concrete problem in the next slide.
Okay.
So that you can see what the question becomes for us. Okay, so just to set some notation, let omega sub ln be the set of these configurations, and m sub ln be the generator of this process. So I'll describe what the generator is with an example on the next slide. So let's look at, let's just consider a simple example with 3 sites and one particle, one tracer particle, and one vacancy. So then there are 6 configurations which I've listed over here, and I've ordered them in this particular way. And so the generator of this process, I will use the physics convention of making things column stochastic. So the generator of this process will be a matrix indexed by the configurations, whose, let's say, ijth entry is the rate of going from j to I. So So because it's column stochastic, you go the other way. So just let's focus on one of these configurations. Let's say the second one. So there are two possible transitions that this can make. So with rate 1, the one on the last site can go to the first site, in which case you jump to configuration number 4. And that is why the 4th row has a 1 over there. And with rate Q, this tracer can move backwards.
Do you mean minus P minus 1, or do you mean minus V plus 1?
No, forget the diagonal entries for a moment. I'll come to that in a second. So let's just look at the off-diagonal entries. So continuing my example, so if for the second column, the second configuration, in the second configuration, this 1 hat can move left, leading to configuration number 5. That happens, that transition happens with rate Q. And so the 5th row here has a Q, okay? So you fill the off-diagonal entries with the rates in the way, in using these 1s and P's and Q's in this way explained in the previous slide. And so you get this matrix. And now to get the diagonal entries, all you do is you ensure that column sums are 0. So that's why there's a minus P minus 1.
So it's column stochastic before you subtract the identity matrix. Is it?
Right, yes, in a way, yes. But these are rates and not probabilities. So you're, I mean, there's a slight issue because these can, so for a discrete time Markov chain, these would all be probabilities, and then you would not do the subtraction. Yeah. Okay. But otherwise, it's, the idea is the same. Okay, so is that clear? I mean, let me know if there's any question. Okay, so let me describe a bit about the history of this model. So this was first studied, as far as I know, by Ferrari, Goldstein and Lebowitz in 1985. And they were interested in understanding something called the Einstein relation. And let me not get into it. It's a major breakthrough in physics.
I have a question.
Please. Should I go back? Yeah. Go ahead, Raghavan.
So what does that minus P minus 1 signify? I mean, I'm bothered by the negativeness of that.
So what it signifies is the total outgoing rate, negative of the total outgoing rate from any configuration. So the off-diagonal entries signify the rates from one configuration to another, and the diagonal entries signify negative of the total outgoing rate. So when we are going to, okay, so I'll just give me a couple of minutes. I will, when I come to the stationary distribution, I'll illustrate this point again, and maybe that will resolve your uneasiness. Is that okay?
Thank you, go ahead.
Okay. So, yeah, so this was first studied in 1985, as I said, to study this Einstein relation, which is one of the, I mean, this was one of the things that Einstein discovered in his Annus Mirabilis, 1905. Anyway, so I don't want to get into it. I mean, there's some physics motivation, if you like. Then some physicists, O'Shannon and his group in Paris studied a very similar model on Z instead. So instead of taking L sites, they took all of the integers. And they showed something interesting, that if you consider the tracer, then and look up till time t, then it goes up to this. It has it goes up to root t rather than t. So which is because of the presence of these other particles. Anyway, so that was
Independent
one.
of the number of particles, is it?
Sorry?
Independent of the number, I guess it's Z, so yeah.
Yeah, it's Z. So there are infinitely many other particles.
Yeah.
And
So how do you initialize? Do you have
yeah, so you can, the way they initialize it is to place the tracer at the origin, and for the others, they do Bernoulli initial conditions. So fix some density rho between 0 and 1 and place with probability rho independently at each other side. And then they see how, so they study both the mean and the variance and things, and the variance goes like root t. And so the particular case when P and Q are both 1 has been studied for a while, since the 80s. And in that case, of course, the tracer is indistinguishable from any other particles. And that's called, it has been called the tagged particle in the literature. And there's a lot of work on it, and I don't want to get into it too much. It's just to mention the connection with other models. And for rigorously, Landim, Ola, and Volchan proved the law of large numbers for this displacement, and later Landim and Volchan proved the CLT. And for a similar process, one can define the analogous version of this process in ZD for NED, and study if the Ashen relation continues to be valid, and it does not for D more than 3. Right? So this, and I should also mention that after my work appeared on the arXiv, there was a paper of Martin Evans and his student Lebowitz, where they study this model with Q equals 0, and many more tracers. So they do more physics study. So the motivation for me was to understand the current. So let me define the current. So suppose so now we are back to our model, and suppose you fix an edge between two sides, and you look at the number of times a regular particle, let's say, crosses this edge in the forward direction, let's say clockwise, and you call that n plus of t up till time t. And similarly, n minus of t is the number of times it crosses in the backward direction. Okay, so you just keep track of this. You just look at that edge and you just see how many times this any particle any of the ones moves forward or backward. And then the limit of this quantity, n plus minus n minus divided by t, as t goes to infinity, is called the current. And it's not too hard to see that this is independent of the edge that you chose. I mean, it's just particle conservation. And so currents are very important for the point of view of statistical physics. And so one of the motivations was to see if you could generate a current. So you see all these regular particles, the ones, are symmetric. So they move forward and backward equally often on average. And but there is this one tracer particle that is trying to push one way rather than the other. So without loss of generality, take P to be greater than Q, greater than or equal to Q. So it's trying to push, let's say, in the clockwise direction. So one wants to know whether one can generate a current for a large system this way. I mean, this is a natural question, and somehow this was not yet studied. So, so now let's see what this station is. So the natural thing to study is to see what happens to the system in the long time limit. So when as time gets larger and larger, the probability of any configuration is given by the stationary distribution. So, so for us, so a stationary distribution is just a probability distribution on the space of, on the configuration space, omega. And for us, our process is both a finite state space and it is irreducible. By irreducible, I mean that you can get from any configuration to any other configuration by a sequence of moves. So if another way of saying it is that if you look at the graph of the transition of transitions, then this is strongly connected. It's a directed graph, but it's strongly connected. So our Markov process, both finite state space, is on a finite state space and is irreducible. So, you know, the general nonsense will guarantee that there's a unique stationary distribution.
Sorry, what is the definition of strongly connected?
Strongly connected, well, in a directed graph, a directed graph is strongly connected if there is a path, a directed path from any vertex to any other vertex. Okay.
Okay.
So by directed path, I mean paths going in the forward. I mean with the arrows in the right way. Yeah. Okay. So the stationary distribution is unique, and you want to understand what it is. So for us,
kind of symmetric in time, right? I mean,
sorry.
The forward steps are the same as the backward steps. Only the probabilities get switched, P and Q. But anyway, never mind.
Yeah. Okay. Yes, but not. No, but that destroys actually. Yeah. So it's not true that the process is reversible. So
yeah. But,
so okay, I will comment on that later. Yeah, I was planning to talk about that. Okay. So the stationary distribution. Computationally is just the eigenvector, the column vector of M, which has eigenvalue 0. So this gives me a chance to answer Raghavan's question. So if you look at the column vector for this example, you want M times V or pi to be equal to 0. And then if you write the equation down, component wise, then, and you take the negative, the term corresponding to the diagonal entry to the other side. So then you'll get that the total incoming rate is equal to the total outgoing rate. That's what this is. So that's why these negative entries are there on the diagonal. Raghavan, does that answer your question?
For now, yes.
Okay. Okay, fine. So yeah, please feel free to ask it. Okay. So for this example, the stationary distribution is given by this vector, and I've normalized it by this quantity, which I'll define later. So the thing I want you to notice, two things I want you to notice. One of them is that the first, fourth, and fifth have the same probabilities, and the second, third, and sixth have the same probabilities. And this is easy to see. It's because the first, fourth, and fifth are translates of one another. Translates, for this example, translation is the same as rotation. So if you rotate the first configuration, let's say to the whatever, right or left, you'll obtain the fourth one, and then if you rotate again, you'll obtain the fifth one. And similarly, the second, third, and sixth are rotated. So that's one property. The other property to notice is, again, going back, if you compare the first and the second, they're just off by, you get one from the other by interchanging P and Q. And that is also sort of easy to see. I'll explain that in the next slide. So the first is this translation invariance, and that's sort of clear because your transition rules do not really depend on where these transitions take place. I could just relabel my configurations. Instead of calling site 1, I could replace the label site 1 by site 2 and 2 by 3 and so on, and the process doesn't see the difference. So stationary probabilities is certainly invariant in the translation, so which means rotation in this case. The
What
other,
are the tau i's?
oh, sorry. So yeah, I should have said that. So tau i's are either 0, 1, or 1 hat. That was my notation at the beginning. So tau I is 0 corresponds to vacancy, 1 corresponds to a regular particle, and 1 hat corresponds.
So this L tuple is a configuration.
Yes, L tuple is.
Okay.
So yeah, so I'm abusing notation slightly. I'm using pi both for the stationary distribution and for this vector. So, but yeah, it should be clear from context. The other property is this reflection invariance, or sort of invariance, is that if you look left to right instead of right to left, and you interchange P by Q, then the stationary probabilities will remain. Yeah, so these are two easy properties one can check. And so to define the main formula, I need some notation. So because of the translation invariance, it is enough to consider configurations where the first site is a 1 hat.
Arvind, I have a question.
Yes.
So I understood translation invariance, but not this other reflection invariance. So
okay.
Could you use the previous example to illustrate this?
Yeah. So look at the first and the second configuration. So I'll go there. So if I read the first configuration from right to left instead, so I'll get 1 hat, 1, 0. And if I translate that a little, I'll get 1 hat, 1, 0 in this way, 0, 1 hat, 1, right? So
yeah.
So the P and Q are exchanged. And this is easy to see because the only thing giving this right-left asymmetry is this PQ transitions. So that also.
Okay, thanks.
Yeah. Okay, so now, as I said, let's consider configurations where the first site is a 1 hat. And then I define the following function, W of tau. I take this product over all sites, and I focus on sites where tau I is 0. And I multiply by 1 plus P times Mi of tau plus Q times Ni of tau, where Mi is the number of ones to the left of that 0. And Ni is the number of ones to the right of that 0. So I'll give you an example in a second. But the main theorem is that the stationary distribution is proportional to this beautiful product formula. So to make this a probability distribution, I have to divide by something. So that's just the sum of the W taus. Okay, so that's called the partition function or normalization.
Can you show the definition of W again? I mean, this is really
I'll go through the example. I'll go through this example and see what it means. So consider the example with 5 sites and 2 particles. So I'm only focusing on configurations where the first site is a 1 hat. Now look at the first 0 in the first configuration. It has 2 ones to its right. So I get a factor of 1 plus 2 cubed. Now look at the second 0. It also has 2
ones. It would be helpful if you could just show us that definition of W once again.
Okay.
Yeah. Okay. So 1 plus P times particles to the right plus Q times particles to the left. Okay.
No, 1 plus P times particles to the left plus Q times.
Oops. Oh, okay. Thanks. Okay. P times, okay, got it.
So now if you look at this second configuration, for this one, for this 0, there are 2 1s to its right. So I get 1 plus 2q. And for this one, there's 1 1 to the left and 1 1 to the right. So I get 1 plus 2 plus 1. Similarly, and so on, you can see. So you know, this is a very nice explicit formula for this, for the stationary probabilities. So this is the equation that I was talking about, Raghavan, when I was
Don't
explaining.
quite understand how the position of the tagged particle, the tracer formula.
Sorry?
So the tracer, how does the tracer play into the formula in W's, in the weight formula?
Good.
What's the role of?
It somehow sets the position where you start to do the counting. So here I can, once I fix the tracer to be at the left side, I can talk about left and right. I mean, without that, I can't really talk about left and right because it's on a cycle.
Okay, thank you.
Yeah. Right, that's a good question. Okay, so because the stationary distribution is unique, the way to prove it is to just verify this master equation. That's total incoming rate is total outgoing rate, and there's some case analysis, and it can be done. But there's another more abstract way of doing this, is to notice that it is related to, I mean, it can be expressed as a zero range process, or whatever that is, and for such processes, this factorization is sort of is there by in general, and then one just has to make some checks. So that's an alternate way of doing this. Okay, so now let me state some properties of the partition function. Well, there's only one tracer, so you know, so under translation, there is no fixed point. I mean, you can translate arbitrarily many times and there's going to be no fixed point. So this partition function is going to be L times a polynomial in P and Q. So, you know, it doesn't, that L, factor of L doesn't buy you anything. So one can just focus on configurations where the first site is a 1 hat and look at that sum. And I'm going to call that the restricted partition function. I'm going to denote it in this funny way. Yes?
Hello?
Okay.
Can
Yes?
you recall the definition of ZLN?
Yeah, it's just the denominator which normalizes the probabilities. So you sum over all weights.
Okay. Yeah. Okay.
So that each pi, so that pi of tau sums to 1 overall.
Okay. Thanks.
Yeah. So I define this restricted partition function with this funny notation, L set n plus 1 PQ. And if you are going to ask why this funny notation, thank you for asking. And so here's the reason. So I'll have to digress a little bit. So I'll recall Stirling numbers for those of you who are not combinatorialists. So let box n be the set 1 through n, and let box n set k be the set collection of set partitions of n, of 1 through n, into exactly k parts. So recall that a set partition is a collection of subsets which are pairwise disjoint and whose union is the entire set. So just to give you an example, the set partitions of 1 through 4 into 2 parts can be written in this way. I've used vertical bars to separate the sets instead of adding more braces, and it just causes confusion. So here 1, 2, 3 is one subset, 4 is another, singleton is another subset, and so on. So you can see that there are 7 partitions, 7 set partitions here, and of this. And then, so the number of set partitions of 1 through n into k parts is known as the Stirling number of the second kind. And there are many notations for this, but the notation I like the most is like the binomial coefficient. So instead of saying n choose k, say n set k. So this is from Knut, Graham, and Dashnik. So the above example shows that 4 set 2 is 7. So this is classical. I mean, this goes back maybe a few centuries.
So, I'm a little confused. So empty is not allowed?
Empty is not allowed. Otherwise, you could keep adding empties. Yeah. Yeah, non-empty subsets. Okay.
Okay, thanks.
So they satisfy an easy recurrence. One can check, and just to give you some data, here are the first few numbers. So I should say unlike the binomial coefficient, there's no simple formula. There's nothing straightforward. And also, I'll just to make a remark, the total number of set partitions is called the Bell number, and it's denoted with sub n. And there are many identities for the Stirling numbers, but even though there's no concrete formula, I mean, there's no simple formula for n set k. So let me focus on, two formulas. One is the column generating function. So the column generating function is just, you fix a k and you sum over, you take the generating function over all n larger than k. So if you look at this ordinary generating function, it has this beautiful product formula, x to the k by 1 minus x1 minus 2x, etc., minus kx. Now you can use your standard partial fractions from high school, and you can then you can expand this out, and you can get, and each of them is just a geometric series. So you can use that to get an explicit formula for the Stirling numbers. Unfortunately, this has signs, so it's not super nice. But the interesting and surprising thing, if you don't think about it too much, is that I can change this k and make it as high as I want, and the answer will not change. So n only appears here in R to the n, and I can change a to be k to be even larger. So at first glance this seems like. But one can use this to get a beautiful bivariate generating function.
Sorry, what do you mean holds when n is less than k? You have defined it only when n is bigger than k.
Yeah, but yes, so this formula as stated holds when n is less than k. But I'm just making a statement that I can replace this k over here, this sum, not these k's, but just this k, I can replace to be arbitrarily high, and it won't change the answer. This is somewhat surprising if you haven't seen it before.
No, I'm sorry, I still don't follow.
Anyway, okay, ignore it. It's just a curiosity. I'm just saying that the summand can be changed. I mean, the sums, the limits of the sums can be changed, and that doesn't affect the answer. It's counterintuitive. But okay, but if anyway, I'm sort of running over time, so I shouldn't dwell too much on this. Sorry, Raghav.
Okay, go ahead.
So consider the bivariate generating function. So now I take a generating function both in terms of n and k, where the generating function n is of exponential type, and the generating function y in k is of ordinary type. Then you get this beautiful formula as a double exponential. It's e to the y times e to the exponential. Okay, so I will refer to this later. So why did I introduce this notation? And that's because if I take the special case p equals 1 and q equals 0, in which case the tracer particle only performs totally asymmetric motion, then you get the partition function. The restricted partition function is the Stirling number. So there's somewhat unexpected connection. And I should say that I should also say that there have been many variants of the Stirling number studied over the years, starting with Carlitz, and you can see many names, and with parameters. In some cases, people like Wachs and White also have studied 2 parameter variants, but this doesn't seem to be any of those. So this is new as far as I know. Okay, and to prove this, I'll consider, one needs to consider a more general case, but maybe I'm running out of time, so maybe I will move a little faster. So let me not prove this for you. There's a combinatorial proof. But let me just focus on other properties. So one thing that you might have seen, you might have noticed, is that the restricted partition function is a symmetric polynomial in P and Q. And in general, so this was Amri's question. So it seems like, the process is kind of reversible. If you kind of interchange P and Q and you reverse time, you should, one would think that you would get back the same process, but that's not true. So, if P is different from Q, this process is irreversible. So and at stationarity. So that follows directly from the formula, from this complicated product formula for the distribution. Anyway, so when P equals Q, the stationary distribution becomes trivial. It's uniform. So every configuration becomes equally likely, and the process becomes reversible. So that's less interesting. But even if P is equal to Q, but they're not equal to 1, but that's still boring. So we'll consider the case P strictly greater than Q. Okay, so then one can show that they satisfy some recurrence. It's a bit complicated. For the second term, you have to change the values of P and Q also. I'm not dwelling on it too much. I'm just trying to say that some properties are known. Now let's look at the column generating function of these guys. So
just a quick question. So you said that when you put P equals 1 and Q equals 0, you just get the Stirling numbers, right?
For the restricted partition function.
And the other way you get
other way, P equals Q?
P equals 0, Q equals 1. You should also get Stirling.
Yeah, it's the same thing. Yeah.
And in between, okay, so you're like.
So we are kind of interpolating.
And P equals Q, okay.
Yeah. Okay, so now consider the column generating function. So I take L, this restricted partition function, I sum over all L greater than N plus 1. Then I again get a nice product formula for these guys. And again, if you said P equals 1, Q equals 0, you will get the column generating function of insect. So this generalizes that. And again, using partial fractions, you can get an explicit, although signed formula. And this is not useful for asymptotics. But of course, if you want to see the value for any numeric P and Q, this is very useful. And here is the generalization of the mixed bivariate generating function of the Stirling numbers. Again, this is a double exponential form. So it's e to the, so here I have taken this restricted partition function. It's ordinary in the n variable in the number of particles and exponential in the number of sites. And notice that I have to do the slide shift. That's just for technical reasons. Then I again get a nice, beautiful double exponential formula. And those of you who are fast at computation, you'll notice that if you set P equals 1 and Q equals 0, you don't exactly get back the same formula as the Stirling numbers, but it's just off by a shift. Nothing serious. Okay, so let me tell you something about asymptotics.
Sorry.
Yeah.
I thought you had an e to the x in the previous one.
Sorry, I mixed notation. Sorry. So, yeah, here it was exponential in x.
I see. Okay.
Yeah, too observant. Yeah, sorry, I messed up the notation. Okay, so let me tell you about the asymptotic. So, from the physics point of view, it's interesting to look at the.
Sorry, Arvind. Still, there one was a y and the other was an x. Here you have both here both are y's.
No, there's an x also here. So this x plays the role of that y, and these things play the role of that x. So this factor is kind of extra.
Okay.
And that's because of some shift.
Thanks. Yeah.
Okay, so as I was saying, let's come to asymptotic. So physicists are always interested in the case where the system size goes to infinity, L goes to infinity, and the number of particles go to infinity, but there is a density of the particles, so that the ratio n by L converges to rho, where rho is between 0 and 1. So this is the typical limit that physicists are interested in. So for that limit, I'll give you the asymptotic formula. So suppose y naught is the unique real positive solution to this equation. E to the p minus qy is rho qy minus 1 by rho py minus 1. Notice that y equals 0 is our solution. Well, okay, if you take the appropriate limit on the right-hand side. But we don't want that. We're not interested in that. There is a strictly positive solution, and that's unique. So that's the thing that we're going to call y naught. Then remember that I took n to be rho L, sort of. And then the asymptotic value of L, this restricted partition function, is given with these prefactors of square root type times some exponential parts. But the thing I want you to focus on is this bit over here, which is of the form L to the L. So it's of like factorial growth, this bit over here, so which is faster than exponential. So to be perfectly honest, I mean, I didn't write this as a theorem because I'm not proved this at the level of rigor that is. I mean, I've not done all my epsilon deltas, but I have verified it extensively. So here's an example. So I take n to be half the system size, half of L, and I take some generic values of P and Q, nothing special. And I take even values of L from 12 to 120. This is the ratio. I've plotted the ratio of the exact formula to the asymptotic formula, and you can see that it approaches 1. Okay, so just to tell you that even though I didn't do all the details super carefully.
When you say that you haven't proved it, have you proved it with a rigor enough for physicists?
Yeah. No, I think I've done more than that. But I have not done it. Let's just say I've not done it to the rigor demanded by analytic combinatorialists, for example, who really are careful. So I cannot give you the error term, for example. What's the order of the error? I'm not done in the system. Okay, so I should maybe quickly say that I'll focus on this case also later, this special case where the tracer does totally asymmetric motion when P is 1 and Q is 0. In that case, the the asymptotics depends on this famous special function called the Lambert function. This is the inverse function of z e to the z. And you focus on the principal branch. It's not injective. So and then if you define G to be this, this funny expression, then there's a simpler formula. This is due to this Dutch analytic combinatorialist Nico Temme, whose techniques I borrow heavily. And again, here you will see an L to the L dependence, which is so the super exponential group. Okay. All right. So as I mentioned, we were interested in the current. So now we have two kinds of particles. There are ordinary particles and the tracers. And so there are two kinds of currents, which I'll call J sub 1 and J sub 1 hat. So if you denote by expectations in the stationary distribution, these angular bracket notation, then J1 is the probability that there's a 1 at the ith side times a 0 at the jth side. Oh, sorry, I should have explained this. So sigma I is 1 if and only if the ith side is occupied by a 1 hat, and tau I is 1 if and only if it's occupied by 1. And otherwise there's 0. So this means that there's a 1 at the ith side and a 0 at the jth side, at the I plus 1th side, sorry. And this means the other way around. So calculating these probabilities will give you the current. And as I said before, this is independent of I. Similarly, the current of 1 hats is P times the probability that there's a 1 hat at site I and a 0 at site I plus 1 minus Q times the other way around. So in the stationary distribution, so the currents have this nice explicit formula. So the current of 1 hat is P minus Q times a restricted partition function of a smaller size divided by the ordinary partition function. And the current of 1s is the same as that of 1 hats with this except for this extra factor. So if you like, the current of 1s and 1 hats are kind of the same if you look individually. And this can be proved directly. This is not hard. So again, using the asymptotics, using the asymptotic formula, one finds that the current of 1 hat goes like 1 by L squared. And so the current of 1, because of this extra factor of n, will go like 1 by L. So as you take L and n to infinity, so that n by L converges to rho, then the current does not survive. So which is not unexpected, because one doesn't expect that if you have infinitely many particles, that a single tracer particle will be able to influence the current. So I should also mention that I'm working on another project with Philippe Nadeau, and we are trying to generalize, to see what happens when there are more tracers. Okay, so densities. So a density is just, the density of a particle at site I is just the probability of having a particle at that site. So because the system is translation invariant, the probability of...
Sorry, Arvind, can we look at your formulas for the current? Please?
Yeah.
The one before also?
Yeah.
So here there is no difference. Oh, there is an n.
Oh, there's an n.
There is an n. Okay.
Yeah. That's just because there are n particles.
Yeah, n more particles. Okay. Makes sense. Okay.
So each particle has the same current.
Correct. Okay. Yeah. 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 Thanks.
Yeah. Okay. So the density is just the probability of having a particle at a given site. So because the system is translation invariant, the probability of having a tracer at any given site is equally likely. And so it's 1 by L. Similarly, for the for the ordinary particle, it's n by L. So it's just from translation invariance, you get it for free. But what we are interested in is studying from things from, or looking at things from the point of view of the tracer. So suppose you are sitting on the tracer particle and you're looking ahead and seeing how the particles look. What is their density from your point of view, from the tracer's point of view? What is the density 1 site ahead, or 10 sites ahead, or 30 sites behind? So this is known as the environment process. And so to compute things like that, one needs to compute the joint probability of having, let's say, the tracer at site 1 and a regular particle at site I. So this this is called a 2-point correlation. And by computing things like that, you can obtain the probability of having an ordinary particle I sites in front of the tracer, for example. So just to set, I'll shift my notation for convenience a little bit. So I'll place the tracer at position 0, and I will look both forward and behind the tracer particle. So I label forward positions by 1 through L minus 1 and backward positions by -1 to -1. Of course, you know, position L minus 1 in front is the same as position -1 behind. You know, that's clear. But we want to take the limit as L goes to infinity, in which case we will get something on Z. So, you know, then they need not be related. So here's our result. It's a bit complicated, I admit. So there's an exact formula for the densities as seen by the tracer, and it's a double sum. It involves some binomial coefficients, and it involves these ratios of restricted partition functions, both ahead and behind the tracer. Excuse me. So the only thing different in these two formulas is that P and Q are interchanged, which also makes sense because of this reflection quasi-invariance. And when P is 1 and Q is 0, you know, the formulas simplify considerably. You just get a single sum. And okay, so now we want to take asymptotic densities. Amri, how much time do I have? Oh, Amri is not there, so maybe I'll take some more time. Okay, so again, remember that we are taking the limit L and N going to infinity, so that N by L converges to rho. And now we'll look at a scaled position. So instead of looking at a fixed position, which kind of doesn't, I'll argue that later that it doesn't make too much sense. You want to take a position that also stretches, that scales with the system size. So I'll fix some X in 0, 1, and I'll focus on a position XL roughly, both forward and behind. And then from our asymptotic formulas, we get pretty explicit formulas. I remind you that Y naught is that solution to that, is a unique solution to some transcendental equation. Okay, so this is pretty explicit. But I want to focus on some of its features. So before that, here's a comparison. So I took, again, because, you know, this is not really rigorous at that level, just to show you comparison with the actual formula. So these are not simulations, by the way. These are, this is a plot of the exact density of particles using the formula, using the theorem in red, and the asymptotic formula in this blue curve. And I've taken large L and some arbitrary values of N, P. Okay, so again, coming back to the special case, P is 1, Q 0, then in that case, using this Lambert function, in front, it goes exponentially, well, sort of exponentially. Remember, X is only between 0 and 1. And behind the tracer, it also has this kind of exponential behavior. But now I want to give you some flavor of what happens. So here, notice that there's no prefactor. In this case, there's some prefactor. Here, there's nothing. So in particular, suppose you focus on what happens just immediately in front of the tracer particle. So it doesn't, well, immediately in front in the macroscopic sense, in this macroscopic scale. So, it could be, 100 sites ahead or whatever. Then what this argues, or what this formula tells us, is that this at x equals 0, this becomes 1. So that means that there will be a particle there with probability 1. So in particular, if you fix any site, let's say 1,000,000, and you look at the 1,000,000th site in front of the tracer, and you look, and you let this L go to infinity, then you will get density 1. So what that means is there's an infinite traffic jam in front of you. Because, and this sort of makes sense because, all the other particles are doing symmetric exclusion, just going equally likely forward and backward, but this particular tracer is pushing you one way more and more. So I got a message in the chat. Okay. So Amri has said it's okay to go over time. Okay. Okay. Fine. Right. So as I was saying, so all the particles are moving symmetrically, but this one tracer is just going asymmetrically. It's just going forward. And so what is going to happen is that there's going to be an accumulation of particles. And in the infinite volume limit, what this analysis gives you is that there will essentially be an infinite traffic jam in front of you. So you'll have an arbitrarily large cluster blocking you. And similarly, because this guy is going forward, only forward, it leaves behind a wake. And because of that, from its point of view, if it looks far enough backward, the density again becomes 1, which is what. So when you take x equal to 1 over here. Okay, so this kind of explains some heuristic picture. Okay, I'm kind of over time, but maybe let me just tell you something about the asymptotics. I'll maybe take a couple of minutes. So when I was trying to understand the asymptotics of this partition function and all these calculations, I tried to see if I can use anything from the literature on Stirling numbers. And it's quite incredible how much has been studied on asymptotics formulas for Stirling numbers. I mean, so you consider n set k, and for each regime there's a different paper, and so you can see over decades, right? You can see the range, and you can see different cases. So first paper considered little o of square root of n, some n minus little o square root of n, then all kinds of regions, and none of them seem to work for me. And because I wanted to take the limit where k scales with n. And Nicoteme gave the first kind of uniform bounds. And and he did it in this paper in '93, both for first and second kinds. And fortunately for me, this was in Wikipedia. Unfortunately, there was an error, and I had to fix it, which I did a little carefully because I didn't want to upset people. Anyway, but he has amazing intuition, and he does something. He does some very clever change of variables, and I have no idea why he did it. And it just the ordinary saddle point will, and very luckily for me, trick works for this more general. With virtually no change. So I really almost copy pasted his argument. Mutatis mutandis works. So I got lucky in this. Okay, so I think I'm done. Thank you for your attention.
Wonderful. So you can unmute your mics and thank Arvind with. So any questions?
I have a question. Why is the density 1 behind the tracer?
Oh, no, it's not. Oh, sorry.
Behind, you said it's 1. What is
No,
that?
no, it's not 1 behind immediately.
Definitely behind.
It's immediately behind. It's not 1, because if you, for example, set x equals 0, you'll get rho g. But it's 0 infinitely far away. Hey, it's 1 infinitely far away.
What does that even mean? I mean,
Does that mean infinitely far away? They will always, like behind some capital N, they will always some non-tracer.
No, I don't think there's anything. No, it's just, I mean, I think it's just sort of this, it's just a sense of scale, right? I mean, if you look from far enough back, it just looks like there's a large cluster of particles there. And that's because it's moving totally asymmetrically. It's having that.
I guess the formulation, the mathematical formulation of that statement is a bit confusing.
Which one?
That infinitely far away to the behind.
Yeah.
I think Sridhar and I both don't really understand what.
No, yeah. So I'm being a little loose here because, I mean, of course, I'm taking limits, and then one has to be careful. I'm just saying that, if you took x equal to 1, this formula, and you just analyze the density behind, you will get 1. So that means behind you, as far behind as you can go, if you're stuck there, then you are almost likely to have a particle. I mean, you're surely likely to. I mean, one can interpret this quite literally, but I'm just saying that, this is a sort. I'm just trying to give a heuristic idea. So, I mean, this is like, if you watch Earth from space, you see, certain parts of Earth are at night. You see certain parts of Earth are brightly illuminated. Well, why is that? It's not because there's one huge light bulb there, right? Paris is highly illuminated. Why? Because it's not because there's one light bulb. It's just because there are many, many, many small light bulbs, and that gives you the kind of impression that there's one. So it's kind of like that, because this tracer particle has moved so far away that, sort of for it, there's like particles. There's almost certainly a particle at any given site far enough. It's sort of like.
Can I ask a question?
Yeah.
Hi, Arvind. Hi, everyone. That was a really nice talk. You mentioned you're thinking about systems with several tracer particles. Like if you had a lot of tracer particles, do you imagine those? You could have a system where they're all sort of spread out in different places, or you could have a system where the tracer particles are all in one block. Like you have n on 2 asymmetric ones followed by n on 2 symmetric ones. What kind of systems are you thinking of?
Oh, so for now we are thinking of finite state space, arbitrarily many traces. So
but do you mix them? Do you intersperse the traces, or do you keep the traces all in one block and the?
well, it's irreducible, right? I mean, it's a finite state space, so it's going to have a stationary distribution.
But
right.
The traces can't overtake the other ones.
That's right. That's right. So that's correct. So tracers can't overtake. So we have a general formula for any arrangement. So you give yourself any kind of arrangement of any number of tracers in between any number of things, and for that there's a formula, and we are trying to analyze the formula. So one of the things that we want to understand is try to see when there is a current. I mean, how many tracers do you need to kickstart a current in the thermodynamic law? So that's one question that I think is of interest even to physicists.
Yeah. That seems like a really nice question.
So that's what we are trying to look at now.
So I've seen similar models with discrete time. So is there some reason for looking at continuous time here?
Well, continuous time in a sense is more natural from the physics point of view. But
Does it matter?
Not so much. I mean, if in the discrete time case, you have to artificially say that there's only one transition at a given time. For continuous time, that's guaranteed for you. So
oh, okay. So this is more elegant, perhaps.
Yeah. So I mean, people do things like this cellular automata and things where you can have all possible transactions that can happen at a given time happen, and then one has to do some prescription. Because there might be overlaps and things. So, but there are these cellular automata versions. No, but not for this model as far as I know. But for the asymmetric exclusion or symmetric exclusions, there have been these things.
Okay, so any more questions?
Yeah, I have one. So I have a question regarding this restricted partition function. They are polynomials with integer coefficients. Whether those coefficients have some combinatorial significance or?
Yes. So right, good question. So yes, so with this, as I mentioned, I was studying this with Philippe, and yes, we now have a combinatorial. Actually, we have a more general Markov chain that projects to this, so that gives a completely combinatorial.
So they are related with the description is in terms of the model that we have.
Sorry?
So the description of the integer coefficients are in terms of the models that we start with?
Yes. Yeah, kind of. I mean, they're combinatorial descriptions. I mean, they say that, the coefficient of e to the I, q to the j is the number of certain configurations, etc., blah, blah, blah. There's some precise.
Yeah, thank you.
Yeah.
Okay, any more questions? Well, I guess if there are no more questions, we can unmute our mics again and then give Arvind a big hand. So that brings us to the end of this session. We'll have one more next week, but the speaker has not been decided yet. We're still looking around for a speaker. So, we saw some new people this time. Welcome. I hope we'll see you again in the weeks to come. So thanks.
Okay. So,
yeah.
see you.
Bye.